The learning objectives for TR-08 are: know the meaning of similar and congruent triangles, know the meaning of corresponding parts of similar and congruent triangles, be able to solve problems using similar triangles. Let's start with vocabulary. Fill in the blanks. Similar triangles have blank angles and blank sides. Congruent triangles have blank angles and blank sides. And the answer we're looking for is not 3. Similar triangles have congruent angles and proportional sides. Similar triangles have the same shape. Congruent triangles have congruent angles and congruent sides. Congruent triangles have the same shape and size. What angle corresponds to angle JLK? We're told the two triangles are similar. There are 2 ways to figure this out. We can examine the diagram and note the angle in the smaller triangle that corresponds to the angle at L. That would be the angle at V. Or we could look at the similarity expression and note that point L is in the 3rd position, so its corresponding angle is in the 3rd position of the other triangle, again V. So the angle corresponding to angle JLK is angle UVT. Expressing this as angle TVU would also be correct. Which side corresponds to line segment MQ? This time we're given a similarity expression but not a diagram. Since the points are listed in corresponding order, we find M and Q in the first triangle and note the corresponding positions in the second. So line segment BT corresponds to line segment MQ. Since we're told these triangles are congruent, we also know MQ is congruent to BT. If we were told the triangles were similar, then we couldn't say the segments were congruent. How long are sides KL and UV? We're told the triangles are similar. The lengths of the sides of the 2 triangles are proportional, so we must determine the constant of proportionality. The only corresponding pair of sides we know are these blinking, so we'll set up the ratio big over small equals 13.1 centimeters over 6 centimeters. This ratio is 2.18, so the ratio of big to small is 2.18 to 1. So KL is 2.18 times longer than TV. 2.18 times 8.9 centimeters equals 19.4 centimeters. And UV is 2.18 times smaller than JL. 26.7 centimeters divided by 2.18 equals 12.2 centimeters. Here's one a little more involved. 3 similar triangles are manufactured from steel beams. The thick beams cost $8 per foot. The thin beams cost $5 per foot. How much does the steel for the 3 triangles cost in total? The thin and thick beams seem to be color-coded for us. We're told the triangles are similar, and we're given some measurements in feet. We need to find the ratio of proportionality between these triangles. To do that, we need to know the measurement of corresponding sides of different triangles. Upon inspection, we have 2 possibilities. We know the thin, green measurements of the large and small triangles, and the bottom measurements of the medium and small. We'll use them both, but let's start with the medium and small. So we can see that the ratio between the lengths of the sides of the medium to small triangle is 11.5 to 3.9, which is 2.95. So the medium triangle sides are 2.95 times longer than their corresponding side of the small triangle. So to find this flashing green side of the medium triangle, we'll multiply the corresponding side of the short triangle, 8.2 feet, by 2.95. That length is 24.2 feet. We can't do anything else with the medium or small triangle just yet, so we need to find a ratio pertaining to the large triangle. We know the green sides of both large and small, so we can find that ratio. Large to small equals 29 feet divided by 8.2 feet, which is 3.54. So we can find the length of the small triangle's vertical side by dividing the length of the large triangle's vertical side by 3.54. That gives us 5.1 feet. We can use that length and the medium to small ratio we already know to determine the length of the medium triangle's vertical side. 5.1 feet times 2.95 equals 15.0 feet. Now there's just one more side we don't know yet. It's on the large triangle, which is 3.54 times as long as its corresponding side of the small triangle. 3.9 feet times 3.54 equals 13.8 feet. So now we know the length of all 9 sides of the 3 similar triangles. But we're not done because we haven't answered the question in the problem statement. How much do the steel beams cost in total? The thick purple beams cost a different amount than the thin green beams, so let's add them up separately. There are 6 thick beams whose total length is 67.3 feet, and there are 3 thin beams whose total length is 61.4 feet. The thick beams cost $8 per foot, and the thin beams cost $5 per foot, so the total cost is $845.40. In this problem, the key was to find the ratios between the lengths of the sides of the similar triangles, and use those ratios to find the lengths of any unknown sides. The rest was just word problem algebra, which you should already be comfortable with, and which you should not forget, because many trigonometry questions can be expressed as word problems. Are these triangles similar? Well, if they're similar, then there will be a constant proportion between the lengths of their corresponding sides. Let's color code the corresponding sides and set up the ratios. So the question becomes, are these terms equal? No, they're not, so the triangles are not similar. The corresponding sides of similar triangles have proportional lengths, and these are not proportional. These triangles are similar. What is h? For similar triangles, we can equate these ratios and solve for h. Simple algebra. Equate these ratios to solve the problem, which is fine, but we could also equate these ratios. Algebraically, they're the same thing. When choosing the numerator and denominator for the ratio between lengths of corresponding sides of similar triangles, you can cross over to the other triangle, or you can use different sides of the same triangle. Let's look at it this way. If there are 4 numbers representing the length of corresponding sides of similar triangles, we can set up ratios like this to be equal. 1/2 equals 3/6. But we could also write ratio fractions like this, and they're equal to each other also. 1/3 equals 2/6. So in solving problems with similar triangles, we can make each fraction's numerator and denominator be part of the same triangle like this, or we can make them be the corresponding parts of the different triangles like this. Use whichever fractions occur to you first. It's usually easiest to make the unknown side the numerator in one of the fractions, so it's simpler to solve.